So I think now we can continue. In this year, we designed strain gauge amplifier and module here. You see it on the screen. And now our software can work with strain gauge sensors. If you have RLC21 or RLC21M, you can use RLS39. It's a strain gauge amplifier. It has 4 channels. And if you have RLC25, you can have this strain gauge module. It's very important to choose your sensors for the test really carefully. While choosing a sensor for the test, it's very important to know the frequency range and maximum acceleration value for the test. First of all, you know that our controller has the voltage limit of 10 volts or 10,000 millivolts. So you can find the maximum acceleration value, which can be got with your accelerometer. You need to divide 10,000 millivolts on your sensitivity. For example, if we have an accelerometer with sensitivity of 100 millivolts per G, so the maximum acceleration value is 100 G. For regular tests, I recommend to use accelerometers with sensitivity of 10 or 100 millivolts per G. But if you're running a shock test with high acceleration values, you need to use sensors with low sensitivity, like 0.1 millivolt per G. So here you see it's the second point. And if you run tests with low frequencies, low accelerations, it's better to use high sensitivity sensors like 1000 millivolts per G. You should remember that sensor selection is really important, and this will help you not to get an overrange channel. In our software, we can connect 2 accelerometer types. We can use regular piezoelectronic accelerometers or MEMS accelerometers. Also, we can run our tests with displacement sensors. We need to use them when we have a really low frequency range in the test profile. We have low acceleration values, but high displacement values. And if you need high accuracy, and it's good to use these displacement sensors during resonance testing, because it doesn't influence the object mass. So you'll get the correct values during the test. In sign test, we also have an ability to use laser vibrometers and triangulation laser sensors. They can be used even as control sensors. And these sensors are widely used in fatigue tests and resonance tracking. The only disadvantage of these displacement sensors is their price. In our software, we also can connect force sensors. They can be used when we have a high load mass or in model analysis. Here on the right side, you can see our model analysis object. It is a metal frame with 4 springs. And here on the bottom, we have a force sensor connected with our shaker. It's really, it can be applied really nice here, because when we run, for example, random test and get impact with a force sensor, it can be really good applied in model analysis. So the main use of force sensors is model analysis with multi-shaker tests, for example, random. In RLC21M, we also can connect temperature sensors. We can use a type K thermocouple or a PT100 temperature sensor. They can be connected on the bottom, on the back side of the controller. And we can display temperature graphs on the screen. And now let's talk a little bit about sensor mounting. It's really important during the test. And if you fix your sensors badly, you'll get errors, emergency stops during the test, and there are 5 main ways of sensor mounting. The most basic one is mounting with a stud. You place a stud in the shaker stable and screw a sensor on it. Also, you can use wax to mount your sensor. You can place a magnet on the bottom of your sensor and place it on the metal. And in some kind of calibration labs, it is usually used with electric isolation base. Here you see on this side our today's hardware configuration. Let me turn on the camera. In today's test, we are running our sine. We have an RLC21 controller, a relay 200 amplifier, and our strain gauge amplifier RLS39. Here we have our regular TV51-110 shaker. We have a beam on it, and we have 3 sensors here. On the beam, we placed a strain gauge sensor and connected it with our strain gauge amplifier. On the top, we have a 10 millivolts per G accelerometer, and here on the right side, you see we have a laser vibrometer. And now I think we can go to our software. For this test, we will run from 5 Hz, and let's set our start amplitude with 2 millimeters. Our end amplitude is 0.3 meters per second. Let's calculate the end frequency. Here you see the value. Let's add another line. We will run this test up to 5G. Let's add the third line. And here, let's enter our final frequency, 200 Hz. And the end amplitude is 5G. In schedule, we will have only one command, it's run profile, but we will run at 60% level. After that, let's check our shaker. Here you see we have Tira TV51-110, and let's set our channels. Let's select the configuration. Let's open it. Here you see that we will run using this configuration, but let's make it a little bit different. On the first channel, we have an IP accelerometer with sensitivity of 10 millivolts per G. On the second channel, we have our laser vibrometer. Its type is linear because it has external power supply, and its sensitivity is 15 millivolts per millimeter. Here we select millimeters. And our third sensor is a strain gauge sensor. And here we need to select strain, microstrain, and press this button. Here we have a strain gauge amplifier, and it is RLS39. Here in bridge supply voltage, we need to set 5 volts. Voltage range will be set as 1. Here, I know that voltage resistance is from the past, but it's 120 ohms. Measuring range will be set as 300 microstrains, and nominal signal output is also from the passport, is 2.17. After that, we press calculate, and here you see that our sensitivity is 10.9 millivolts per strain. We press OK, and here you see that's our strain gauge sensor. Let's apply settings and press OK. Here you see that it's selected 10 millivolts per GIPE, its control, 10 millivolts per millimeter, and our strain gauge sensor. After that, we need to disable the fourth channel, and let's apply the settings. Oh, I think we have two outputs. Let's disable it. Yes. Here you see our profile. And now I think we're ready to run the test. On this acceleration graph, you'll see data from the strain gauge sensor, but it is shown not in G, in microstrain, so it can be a little bit lower than the main line. I think that you see that now we are moving. Let's select the second channel. It's our laser vibrometer. And here in the bottom, you see that we're measuring data from our strain gauge sensor. During this test, we'll get some resonances, and we need to check if our laser vibrometer and strain gauge sensor have the same frequencies. So I think it will be in the end of the profile about 200 Hertz or 160 Hertz. Let's open oscilloscope. And you see that we're measuring from all our channels. We have an option to control the test with laser vibrometer. To do this, you need to set your channel with the laser vibrometer as control and enable one feature in the test settings. I'll show you this option while we will, when we will stop the test. But we have such an option, and this option is also used in fatigue and advanced sign tests.
One question concerning the test safety. So, is there a cable damage control?
Yes, we have cable damage control for RLC21 and RLC21M, and it's supported with IP sensors.
All right. One question from Yunus. Is this phase difference between channels is normal?
Yes, it's okay. And about this phase difference, it's okay because we have sensors on different sides of our beam. For example, our control sensor is placed on the center of the shaker stable, and our laser vibrometer and strain gauge are placed on the beam. Let's go back to our test. Here you see that with the laser vibrometer, we found some resonances. And here with the strain gauge, you see that the value is rising, and it's rising with a laser vibrometer. And I think we're really close to our resonance peak here. Here you see that we got really high acceleration values. And let's add the cursor. And I think we have resonances on the same frequencies. And I think that now we can stop the test. So you see that you can run tests with different sensor types. Like here we used an IPE sensor. a laser vibrometer, and a strain gauge. So let's go back to our presentation. Sorry, I was asked about the control. Here in sign test, in control tab, you have a control switch limit option. That means that we can have a control from our start frequency up to this value, and we will control our test with a non-accelerometer sensor. For example, if we need to control the test from 5 Hz up to 30 Hz with a laser vibrometer, we select it as control and enter here our final frequency value. So let's go back to our presentation. And about strain gauge sensor sensitivity. It is calculated automatically in our software, but you need to have some data for this calculation. First of all, you need to know the sensitivity unit. In our case, it's microstrains. We need to know bridge power voltage. We need to know gauge factor and the measurement range. All these data are shown in the sensor passport. And now let's talk about the common mistakes during the sensor setup in our software. First of all, you need to check that in your channel settings you have correct sensor types. For example, you have 3 IP sensors. They are connected, but in software you have linear sensor type. It's a huge error, and you can damage your equipment in that way, because the system will get a response, but it will be much lower, and we can try to control with these low values. In that case, we can have errors, emergency stops, so you need to check sensor types. After that, you need to check the sensitivity. You need to place it in the units, and its value must be from the sensor's passport. Another error or mistake you can have during the test is a bad fixture. You need to screw the sensor or place it really hard, because during the test you can have resonances, high amplitudes, and in that case you'll receive bad data. And you need to select correct sensors for the test. For example, if we have, as I mentioned earlier, for shock tests, it's better to have low sensitivities, because if we have, for example, 200G shock, but we have 100 millivolts to G accelerometer, our sensor will get an overrange, and in that case we'll receive errors during the test. Do we have any other questions?
Yeah, as a matter of fact. So one question is, can we calibrate sensors using our software?
Yes, we have a calibration module, and I made a webinar about calibration, and my colleague Dmitry also make some educational videos about calibration.
Right. I should just add that our software supports automatic report generation. It can support multiple shakers to cover even the highest ranges. And we also use random vibration to lower the calibration time to less than 4 minutes. So it's perfect for mass production.
Yeah, I'm really proud of our calibration module.
One question from Yunus. Can we make control by using strain gauge also?
I think that now we can do it, but we develop this option now and improving it. I think after the new year, we will make a video or some kind of paper about strain gauge sensors, their connection, and using them in the test. And now in this version, we can use strain gauge to for control only in sign and fatigue tests. But I think in the future we will develop this option.
All right, thank you. And one more question. Can we connect tachometers to the system?
Tachometers can be connected, but only to RL19. For RLC21 and all kinds of our vibration controllers, we cannot add tachometers here.
All right.
And I think that in this webinar, we learned about all kinds of vibration sensors which can be used with RULA devices. I mentioned that in this year we introduced strain gauge and we expanded the range of applying strain gauge. In this webinar, we learned how to choose sensors for the test, connect them, and I told you about the most common mistakes during the sensor setup, and now you know how to avoid these errors. I think that's all I wanted to say about the sensors, and thank you for joining us, and Happy New Year and Merry Christmas.